the ground beneath our feet is, it's basically a black box.
Right.
Usually when we look at a massive construction site, like a skyscraper going up or a hydroelectric dam or a new underground mine, we tend to focus on the sheer scale of the engineering on the surface.
Oh, absolutely. The cranes, the concrete, all of that.
Exactly, the thousands of tons of steel. But the reality is, all of that multi-billion-dollar surface engineering is completely dependent on something incredibly fragile. So today on the deep dive, we're opening that black box.
Yeah, we are.
We're looking at a training document, Module 1, Introduction to Diamond Drilling. And we're going to see why the fate of massive engineering projects hinges entirely on recovering a simple, delicate cylinder of rock. Because, for the listener, by the end of this deep dive, you'll understand why millions of dollars all come down to this one pristine sample.
It really is an industry that operates almost entirely out of sight, yet it dictates literally everything built on top of it. Because when we talk about drilling, the default assumption is excavation, right? Like you want to make a hole in the ground to put something in it or, to get something out, like oil or water.
Right, like a well.
Exactly. But the materials we're diving into today, they completely flipped that premise. Diamond drilling, it isn't about the hole at all.
Wait, really?
Yeah. The hole is literally just the byproduct. It's the waste. The actual objective is extracting a continuous physical, pristine record of the Earth's hidden structure.
Okay, so let's get straight into the mechanics of this. The text talks about a method of rotary drilling that uses an annular or, ring-shaped drill bit embedded with industrial diamonds.
Yep.
Now, anyone familiar with heavy industry knows diamonds are used because they're at the absolute top of the Mohs hardness scale.
Right.
But how exactly does this bit survive? I mean, if you're grinding through solid granite or quartzite thousands of meters deep, even diamonds are going to wear down or shatter under that kind of friction and heat, right?
Well, yeah, and that's the genius of the tool's design. It comes down to metallurgy.
Okay.
Because the diamonds aren't just glued to the surface of the bit, they're impregnated throughout a metallic compound called a matrix.
Oh, okay.
And here's where it gets, highly technical. The physical properties of that metal matrix, they have to be perfectly calibrated to the specific rock being drilled.
Interesting.
Yeah, because if the matrix is too hard, the metal won't wear away. The exposed diamonds will eventually just polish smooth, they'll stop cutting, and the bit will just uselessly rub against the rock.
Oh, wow. So you actually want the bit to disintegrate.
Exactly. You want controlled disintegration.
That is wild.
It is, yeah. As the bit rotates and the friction builds, the rock gradually wears away that metal matrix. And this continuous erosion essentially strips back the layers of metal, constantly exposing sharp, fresh diamonds underneath.
So like a self-sharpening mechanism.
Right, but if the matrix is too soft, it wears away too fast, the diamonds fall out prematurely, and you ruin a very expensive bit.
Yeah, I can imagine.
But if it's perfectly calibrated, the bit cuts a perfect ring into the rock, preserving that solid center.
Which gives us our drill core.
Exactly.
It's basically like using an apple core instead of throwing the whole apple into a blender, right? You want that intact center to see exactly what's inside without destroying it.
That is a perfect analogy because it establishes the core philosophy we found in the source documents. And it's a huge insight, really. Drillers aren't drilling for rock. They are drilling for information.
Wow. Okay. Drilling for information.
Yeah. Which fundamentally changes the objective of the rig. If you're drilling for information, your product isn't a deep hole. Your product is data. Geologists, engineers, they need to see the continuous subsurface record exactly as it exists in the ground.
Right, without blowing it all up.
Exactly. They need to analyze the mineralization, the angle of the faults, the microscopic fractures, all without having to excavate millions of tons of earth just to take a look.
But, I mean, the approach to getting that data has to shift entirely based on who is asking for it, right?
Oh, totally.
Because the documentation outlines three very distinct missions here. We've got exploration, geotechnical, and production drilling.
Yep.
Let's start with exploration. This is the mining sector, looking for viable mineral deposits. And they're going deep. Like the text mentions boreholes pushing past 2,000 meters.
Yeah, they go incredibly deep. And for exploration, the mandate is maximum core recovery and absolute geological accuracy. Because when a mining company is deciding whether to sink, $1 billion into a new shaft, they base that entire economic model on the chemical assay of those core samples.
Wow. So it all hinges on that one sample.
Every single meter of core is analyzed to determine the grade of the ore. If you grind up or wash away even a fraction of that core during the drilling process, you are artificially altering the data the geologists rely on.
That is a ton of pressure on the driller.
It really is.
But then you pivot to geotechnical drilling. Now, this isn't about finding gold or copper. It's about evaluating the structural integrity of the ground for civil engineering. Building bridges, tunnels, dams.
Right.
But wait, with modern technology, can't we just use like ground-penetrating radar or seismic surveys? Why do we still need to physically drag heavy cylinders of rock to the surface?
That's a common question, actually. But it's because a seismic wave or a radar shadow can't be crushed in a laboratory.
Yeah, I guess that makes sense.
Geophysics can give you a rough map of the anomalies down there, but it cannot give you the precise mechanical properties of the rock. An engineer designing a dam needs to know the exact compressive strength of the bedrock.
Like, will it shatter under 1 million tons of concrete?
Exactly. They need to evaluate groundwater conditions, weathering, and this critical metric called rock quality designation, or RQD.
Okay, let's break down RQD because the sources say this metric dictates massive engineering decisions. How exactly is it calculated?
So RQD is a standardized measurement of the degree of fracturing in a rock mass.
Okay.
When the driller pulls up a core run, say a standard 1 meter length of core, the engineer physically measures the pieces. And they only sum up the length of the solid, intact, cylindrical pieces that are longer than 10 centimeters.
Wait, so if the core comes up highly fractured, just like crumbling into gravel-sized chunks, none of those pieces count toward the RQD?
Right, none of them. So if you pull up a meter of rock, but it's shattered into tiny pieces, your RQD might be, 15% or 20%.
Oh, wow.
And that is a massive red flag. It tells the civil engineer that the bedrock is highly unstable. If you try to anchor a suspension bridge into rock with a 20% RQD, the ground is going to shear and the bridge will fail.
So you really need that physical core in your hands to verify it.
You have to. There's no replacement for it.
Which brings us to the third mission, which is production drilling. And this is where the whole paradigm shifts, right?
Oh, big time.
Because you're in an active mine preparing the rock for blasting.
Right.
And suddenly, nobody cares about the core anymore.
Not even a little bit. In production drilling, the geological modeling is already done. Now, the goal is purely excavation.
Just moving rock.
Exactly. The driller is using systems that create rock cuttings, just completely pulverizing the material. It's all about high-speed penetration, hole accuracy, and blast pattern consistency.
So they just want to drill as many blast holes as efficiently as possible to keep the cycle moving.
Right.
So if a driller switches from an exploration job to a production job, their entire mindset has to snap. Like they go from being this careful scientist protecting a sample to basically a speed demon just making holes.
It's a totally different mindset, yes. And the sources highlight this as a crucial insight. You have to know what business you're in.
Yeah.
Because an exploration driller is a data gatherer. A production driller is a rock breaker. The machinery might look identical in some ways, but the mission changes everything.
But that makes me wonder if production drilling where you just pulverize the rock is so incredibly fast and efficient, why use the slower diamond coring method for exploration at all?
Whoa.
I mean, the text compares diamond drilling to other heavy hitters like rotary, percussion, or reverse circulation, or RC drilling, and those are massively productive.
They are, and they definitely dominate other industries. Like, look at standard rotary drilling.
Yeah.
You use these large cutting teeth or rolling tricone bits to crush and scrape the rock.
Right.
And then you pump heavy drilling mud down the hole to flush those small fragments back to the surface. It's exactly how oil, gas, and water wells are drilled.
Super fast.
It's fast, it's effective at opening a large diameter hole, but it completely destroys the rock structure.
Right. And then you have percussion drilling, which is essentially taking a massive pneumatic hammer to the bottom of the hole. Just violent, high-energy impacts, fracturing the rock, great for blast holes, terrible for science.
Exactly. And then there is reverse circulation, RC drilling. This one is very popular in preliminary mineral exploration.
Okay, how does that one work?
It uses a dual-wall drill pipe. So they blast compressed air down the outer ring, which drives a pneumatic hammer that shatters the rock.
Okay.
The air then forces those rock chips up through the inner tube to the surface at incredibly high velocity.
Wow, okay. So with RC, you're getting the rock chips back incredibly fast, and they're uncontaminated by the walls of the hole. But it's still just a pile of chips.
Yep.
It's like taking a sledgehammer to a complex jigsaw puzzle. I mean, you know all the pieces are there, but the picture is completely gone.
That's close, but it's actually much worse than a jigsaw puzzle.
Wait, really? Worse?
Yeah, because with a jigsaw, you at least have all the pieces to work with. With rotary or RC drilling, the chips are completely mixed together over a given interval. You lose the entire spatial relationship.
Oh, I see.
From a pile of loose chips, you cannot observe the precise angle of a fault line. You cannot see the structural orientation of a gold-bearing quartz vein.
Because it's just a pile of dust and pebbles.
Right. You have no idea if a mineral was dispersed evenly through a meter of rock or concentrated in a single 2-millimeter fracture.
So you literally lose the physical context of the Earth.
Exactly.
Huh.
I mean, you can run chemical tests on the chips to know the gold is there, but you have no structural data to tell you how it's deposited. So, diamond drilling is undeniably slower and more expensive per meter. But, a production driller celebrates meters drilled, while an exploration driller celebrates meters of high-quality continuous data.
That makes total sense. Which brings us to the actual physical condition of that data. So we've managed to cut this perfect puzzle piece 1,000 meters underground.
Yep.
The driller now has to pull it up. The sources emphasize this critical metric of core recovery, which is a strict mathematical ratio. Like, if you drill a 3-meter run and you only pull up 2.7 meters of core, you have a 90% recovery rate.
Right, which means 10% of that interval was either ground into powder or just washed away by the drilling fluid.
So you lost 10% of your data.
Yeah.
But the text also makes a point that condition matters just as much as recovery.
Yeah.
I mean, you can have 100% recovery, but if the core looks like it went through a wood chipper, it's useless.
Oh, completely useless.
So how does a driller actually control the condition of the core when the bit is a mile underground? I mean, they can't see it.
It is an entirely sensory and mechanical balancing act. The driller is standing at the control panel managing this highly complex hydraulic and rotational system.
Right.
They have to balance the RPMs of the drill string, the downward feed pressure, and the flow rate of the water cooling the bit. And they're doing all of this based purely on the tactile feedback of the machine.
Wait, so they're literally feeling the ground conditions through the vibration of the rig?
Yes, exactly. If the driller hits a fractured fault zone, the rock inside the core barrel can break apart and jam.
Oh, wow.
And when that happens, the driller will instantly see a spike in hydraulic pressure or feel a sudden erratic jump in torque.
And they have to react immediately.
Instantly, because if they don't adjust their feed pressure or water flow right then, the rotating bit will just grind that jammed core into gravel. A highly skilled driller reads the gauges and feels the vibration to constantly adapt to geology they can't even see.
That is incredible skill.
Yeah.
And once that core is safely brought to the surface, the chain of custody begins. And this process is rigid.
Oh, very rigid.
The core is extracted from the inner tube and placed into compartmentalized trays called core boxes. And the text says it has to be laid out in the exact sequence it was drilled, reading like a book from top left to bottom right. It's measured, labeled with precise depth blocks, and transported for logging.
And this cannot be overstated. The integrity of that sequence is everything.
Which makes me wonder, honestly, about human error. I mean, the guys on the rig are working 12-hour shifts in the freezing cold or extreme heat, handling wet, heavy rock.
Yeah, fatigue is real.
What happens if someone accidentally drops a box? Or, like, puts the core in backward while moving it from the tube to the tray? It sounds like taking the pages of a vital history book and just shuffling them.
It is catastrophic, literally catastrophic, because if you flip a piece of core upside down, you reverse the orientation of every single geological structure inside that piece.
Oh, no.
Yeah. So a fault line that dips 45 degrees to the north suddenly looks like it dips 45 degrees to the south.
And the geologist logs that.
The geologist logs that incorrect data. The engineers input that incorrect data into their 3D block models.
And suddenly, the mining company designs a multi-million-dollar tunnel that completely misses the ore body.
Or worse, they might intersect a high-pressure fault line they modeled incorrectly, risking a cave-in.
All because one piece of rock was placed backward in a wooden box.
Exactly. The core is the permanent product. That chain of custody is sacred on a drill site.
Wow. Well, protecting that fragile sequence requires a highly choreographed mechanical rhythm on the rig. To get this core out of the ground continuously, drillers follow a very specific cycle with a very specific language.
They do, yeah.
The terminology alone is fascinating. Let's walk through the physical mechanics of a drill run.
Sure. It's a continuous repeating loop. First, you have collaring, which is basically starting the hole at the surface.
Okay.
Getting a perfectly stable, straight collar through the loose surface soil and into bedrock is vital, because any slight deviation at the surface will amplify into a massive trajectory error 1,000 meters down.
Just basic geometry.
Exactly.
Once collared, they move to advancing the hole, literally spinning the pipe, pushing the diamond bit into the rock and flushing the cuttings. And the core is sliding up into this protective cylinder inside the drill pipe called the core barrel.
Right. And once that barrel is full, which is usually after about 3 meters, you have completed the run. Now comes the retrieval. And this is where we have to talk about the mechanical brilliance of the wireline system.
Yes. Let's dive deep into wireline because this blew my mind. Historically, in a conventional system, if you're drilling a hole 2 kilometers deep and your 3-meter core barrel was full, how did you get the rock out?
It was a nightmare. You had to physically pull the entire drill string out of the hole.
All 2 kilometers of it.
All of it. You pull up a length of heavy steel pipe, unscrew it with heavy wrenches, stack it on the rig, pull up the next length, unscrew it all the way down to 2 kilometers just to get the core barrel at the bottom.
That sounds agonizingly slow. You'd spend 12 hours just unscrewing and screwing steel pipes together for a few minutes of actual drilling.
It was incredibly inefficient, and the constant removal of the pipe actually destabilized the hole, increasing the risk of a collapse.
Oh, because the walls cave in without the pipe.
Right. But the invention of the wireline system completely revolutionized the industry. In a wireline system, the main drill string, the outer pipe, it just stays in the ground.
Okay.
It acts as a permanent casing, keeping the hole open and stable. The core barrel itself is an independent inner tube that locks into place just behind the drill bit.
So when the inner tube is full of rock, instead of pulling the whole pipe, the driller sends down a specialized tool on a steel cable, a wire line.
Exactly. It's called an overshot. The driller releases the overshot down the inside of the drill pipe. It relies on gravity and water pressure to travel all the way to the bottom.
Down 2 kilometers.
Yep. And when it reaches the inner tube, it physically clips onto a specialized locking mechanism.
Just clicks right in.
Clicks right in. The driller then engages a high-speed winch, releasing the inner tube from the bit, and rapidly hoists just the inner tube full of core to the surface.
That is just brilliant engineering. I mean, you pull the tube, empty the rock perfectly into the core boxes, send the empty inner tube back down inside the pipe, it clicks back into place at the bit, and you immediately resume drilling.
Yep.
You've turned a 12-hour process into a 30-minute process.
It is brilliant. And managing this continuous high-pressure cycle requires a language built for speed and safety, because the communication on a rig floor has to cut through the deafening noise of diesel engines and hydraulic pumps.
Right.
So when they are physically lowering or pulling drill rods out of the hole, it's not called raising or lowering. It's called tripping. You trip in or you trip out.
And when they're actively cutting rock, it's called making hole.
Yeah.
And I think my favorite term is tagging bottom, because you can't just drop heavy steel to the bottom of a hole and immediately start spinning it at 1,000 RPMs.
No, definitely not.
You have to carefully lower the string until you physically feel the bit gently bump the bottom of the borehole. You tag bottom, confirm your depth, establish your water circulation, and then you start making hole.
It's very precise. But out of all the terminology, the one that carries the most dread on a drill site is fishing.
Right. When the average person hears fishing, they think of a relaxing weekend activity on a lake. But on a diamond drill rig, fishing is a high-stakes nightmare. This happens when you drop something down the hole.
Or when something breaks. Like if the sheer torque snaps the steel drill pipe 1,000 meters down, the top half comes up and the bottom half, along with your highly expensive diamond bit and core barrel, is left sitting in the hole.
And that broken equipment is now called a fish.
Exactly.
So now the driller has to blindly fish down a tiny, dark, 2-kilometer deep hole trying to hook a broken metal tube. How do you even begin to do that mechanically?
It's tough. You have to trip the entire drill string back out, remove the bit, and attach a specialized fishing tool. Usually it's a hardened steel tap with aggressive tapered threads. You trip all the way back down until you tag the fish. And then, using the rig's hydraulics, you have to carefully apply downward pressure and slowly rotate, attempting to blindly thread this tap into the broken jagged inside of the lost pipe.
Oh my God, it sounds incredibly tense. You are relying entirely on the hydraulic gauges to tell you if the metal threads are biting into the steel.
Completely blind.
And if you apply too much torque, you just strip the metal
Yeah.
and you lose your grip.
It is agonizing. Fishing can take days or even weeks. You pull tension on the rig, literally stretching the drill rods, just waiting to see if the fish breaks free from the rock or if your tool slips.
And what if it doesn't break free?
If you cannot recover the fish, the hole is dead.
Wow.
You have to cement it up, abandon it, and start over from scratch. Millions of dollars and months of work can be lost purely because of a snapped rod.
Which brings us to the final, unifying insight from the training module. Diamond drilling is a continuous cycle, not a single task. A good driller doesn't just focus on the immediate step. They are thinking chronologically.
They have to. While the machine is making hole, the driller's assistant is already preparing the overshot for the retrieval.
Thinking one step ahead.
Always. While the core is being emptied, they are already inspecting the next drill rod to ensure the threads aren't compromised to prevent a fishing job in the first place. Learning this cycle and speaking this specialized language flawlessly is how a new crew member survives and earns respect on the rig.
We've covered incredible ground today. We started by dispelling the myth of the tool itself, looking how an engineered matrix of industrial diamonds intentionally wears away to carve out a pristine, unbroken cylinder of rock.
Yeah, such a cool concept.
We explored how the mission changes the mindset from the production driller who just needs to blast a hole to the exploration and geotechnical drillers who are essentially data custodians, protecting the integrity of the rock above all else.
We dove into the rigorous zero-tolerance chain of custody, how a single misplaced rock in a core box can literally derail a multi-billion-dollar engineering project. And we broke down the rhythm of the rig, the mechanical brilliance of wireline retrieval, and the high-tension reality of tagging bottom and fishing blindly in the deep earth.
It is a profound process when you really step back and look at it. The men and women running these rigs are capturing a continuous, tangible record of the Earth's deep past. They're pulling up sequential cylinders of history, going back millions of years, reading the tectonic violence and the silent mineralization of a world long before us.
It really is like reading a time capsule.
It is, and it leaves me with this lingering thought. Drillers today are pulling up the Earth's history layer by layer right on that. It makes you wonder, what will the core samples drilled thousands of years from now reveal about the chaotic, concrete layer of history we are leaving behind on the surface today?